Good morning. Thank you for joining the meeting. So last Thursday, we started chapter 5, and we covered the two solution methods for the transient conduction of a body. The pace was pretty fast. So today, I'm going to use the first half of the lecture to give a review and then work on one of the examples that involve the method that we learned last time. And for the second half of the lecture, we will switch to a new topic, the transient conduction in a semi-infinitive solid. So that's my plan for today's lecture. So let's get started. So the problem that we are looking at is the transient conduction of a body. So the red indicate body at time t equal to 0. It has an initial temperature T sub I. And the property of the body, including the density, rho, the volume, capital V, the specific heat, C, and the thermal conductivity, K. So all these are the property of the body. Okay, so these have nothing to do with the fluid. For fluid, we need to know the convection coefficient H, the ambient fluid temperature T sub infinity. At T equal to 0, that's the initial condition. And at T greater than 0, we would like to know what the temperature at the location X, and also what is the amount of heat being transferred out, so QT. So those are the two questions that we're interested in. To find the heat being transferred, QT, if the body has a uniform temperature, so T at any location of X is independent of position. So it's only T is only a function of time. So that's a uniform assumption. So that's a uniform temperature. So if that's the case, then the amount of heat being transferred is simply equal to rho T multiply volume multiply the T initial minus T at that time instant. And this T is also equal to the T average because the body has a uniform temperature, so the average temperature is equal to the temperature T itself. Okay? But if this assumption is not valid, if we cannot assume a uniform temperature, then the amount of heat has to be calculated with the integral. So this integral has to be rho C multiply dV, that's a small volume, multiply Ti minus T at that particular volume. So this X corresponding to this small volume, and the integration has to be taken over the entire volume. So that's a general expression to find the heat being transferred when we have a temperature dependent on the location X. So if T is a function of both X and T, okay? So this is very important. So if you have a non-uniform temperature, you have to use a second formula to determine the Q. And the two methods within the LHC or lumped heat capacitance method, and it only applies to the Biot number based on the characteristic length, the Bi sub C, to be less than 1, much less than 1. Ideally, it would, we would prefer Biot number to be less than 0.1. And the Biot number Bi sub C is defined by this formula, and this equation L sub C equal to volume over A sub S allow us to determine the kinetic length. And A sub S is called active area. So active area, which means the area that involves convection. So if you cover certain area with the insulation, then it cannot be counted as active area. So active area has to be the area involved convection. And the solution for LHC method is very simple. So for temperature in terms of theta, in terms of real temperature, big T, so these two equations are for the temperature profile. And the amount of heat being transferred is given by this equation. And the Q naught is the maximum heat can be transferred. So this is the LHC method. And the second method we learned is called the exact solution. And the advantage of this method is it works for any Biot number. So we don't have any constraint on the Biot number. But the limitation is, since the exact solution involves many terms, so it contains infinite number of terms. And to simplify the solution from infinite term into one term, it requires the Fodor number to be greater or equal to 0.2. So if Fodor number is greater than 0.2, then we can just determine one term, and we call that one-term exact solution. Okay. So for one-term exact solution, the T cannot be very large, so small, or T cannot be small, so it's for larger T, such that Fodor number to be no less than 0.2. So we can use one-term solution. Okay. So that's one limitation. The other limitation is the solution we have found only for certain simple geometry. And if you recall, we have the solution for a plane wall, for a long cylinder, and for a sphere. So those are the three solutions we're able to work with. Okay. So it's only applied to simple geometry. For more complicated geometry, such as the conduction in a cube, for example, we have to rely on numerical method. There will be no simple exact solution. And if we are confirmed that we can use one-term solution, then the temperature at the center, so remember the symbol theta star, which is the dimensionless temperature, we add a subscript naught to indicate the temperature at the center. It can be either center line of a plane wall, or a center line of a cylinder, or a center of a sphere. Okay? So the naught subscript naught indicates the center line or the center. And for a plane wall, the dimensionless coordinate is x star, which is equal to x over L sub c. For a cylinder or a sphere, r star, which is the dimensionless coordinate, equal to r over r naught. And then once we have the theta star naught, which is the dimensionless temperature at the center, we can find the dimensionless temperature at any location based on the geometry. If it's a plane wall, then we can use this equation 5.43b. If it's a long cylinder, we have our equation 5.52b, and etc. So that's so these are the exact solution for three simple geometries: plane wall, long cylinder, and a sphere. And in particular, when we deal with a long cylinder, it involves the Bessel function, J sub naught J1. you can either find these functions from table B.4. This is a table in the appendix. Okay. Or you can find these values from online calculator. So I will show you there is an online calculator allow you to get these special function values. Okay. So later on I will tell you which website allow you to find these special function values. Okay, so this is these are what we have learned on last Thursday. We didn't get a chance to solve an example, so today I'm going to provide you with one example that involves two methods. So here we have a long steel cylinder. So this is a long steel cylinder. So L is much larger than the diameter of the cylinder. Initial temperature T sub I equal to 300 Kelvin. The steel property, density, thermal conductivity, specific heat, and thermal diffusivity are given. Now, please note, you don't need all these four properties. If you are given low CK, then you can find the alpha using this relationship, okay? Or if you are given alpha and K, you can determine low C using this equation. So low C will be equal to K over alpha. So you don't need to be given all these four parameters. Either 3 or 2 will do the job. Now we want to determine the time when the temperature at the center line. So we want to know the time T when the center line temperature are equal to 0. T is a known T is the one we want to find, equal to 800 Kelvin. 800 Kelvin. So what is this time T such that at the center the temperature equal to 800 Kelvin? So that's the first part of the question. The second part is to find the thermal energy gained per unit length. So that will be Q prime at that time instant T. Yeah. So let's start with the LHC method. First, we need to check the Biot number. And to find the Biot number, we have to calculate the kinetic length. Now, for cylinder, it's 1/2 of the radius, or equal to 1/4 of diameter. Okay. And the diameter of the cylinder is 0.1 meter, so divide by 4, that's 0.025 meter. So now we can proceed to find the Biot number based on this kinetic length, so equal to H L sub C over K. K has to be the thermal conductivity of the cylinder, which is made of steel. So K has to be the K of the steel. So H 100 given right here. So 100 multiplied 0.025 divided by K of the steel, 51.2. So 51.2. And the numerical value has to be 0.0, let's see, 2 multiplied 2, close to 0.05, I think 488. Okay. So which is less than 0.1. So that's nice. So now we are pretty sure LHC method is applicable. So LHC method is okay because we have a small Biot number. And the first question is to find the temperature T, find the time such that the temperature at the center, so I equal to 0, at this time T will be equal to 800 Kelvin. So that's the first question. So what is this time T? So we only have one equation relate the temperature T with the time, the lowercase t. Okay, so the T theta over theta I, which is in terms of big T, it's equal to T 800 Kelvin minus T infinity divided by Ti minus T infinity. Okay, so that's the definition of theta over theta I. So let's plug in the values of each T. So 800, the cylinder is being heated at ambient temperature 1200. So T infinity is 1200 divided by T sub I, that's 300 minus 1200. Okay, so denominator is minus 400, numerator is minus 400, denominator is minus 900. So 100 cancel out, so 4 over 9. Okay. And then relate this to time t by the potential function. Okay. So now we take natural log of this equation. So we have t equal to natural log. Since there is a minus sign, so we have to flip 4 over 9, make it 9 over 4 to cancel out the minus sign. So this gives us a numerical number, multiply the time constant tau. Okay, so natural log of 9 over 4 is 2.25. Multiply the tau, which is low v c over h a sub s, but v over a sub s equal to L sub c. I can write this expression using a simplified form or simplified expression. So rho c multiply L sub c. L sub c for a long cylinder is 1/2 of the radius, or 1 over 4 the diameter. Okay, so 1 over 4 multiply diameter. I put a 4 in the denominator, so 4h. Okay. So d equal to 0.1 meter. Rho and c are given, h is also given. And then use the calculator to find the natural log of 2.25. Or you can calculate the time constant first. Okay. Actually, when I did the calculation, I found the tau first, which equal to 1059 seconds, and then multiply natural log of 2.25. So the final solution for the time is 859 seconds. So that's the time it will take for the center line temperature to be 800 Kelvin. Okay. So that's the first part of the question, to find the time. The second part is to find how much thermal energy being transferred into the cylinder. So equal to rho Vc multiply Ti minus T infinity. That's the maximum amount of heat being transferred. So Q naught multiply 1 minus Et over tau. Okay. And the Et over tau equal to, look at this equation, Et over tau can be substituted using 4 over 9. And Ti is 300, T infinity 1200. So we have all the, we have all the values. So the final result equal to minus 1.664 multiplied 10 to 7. And one, I have to point out one important factor. For cylinder, we need the length of cylinder to find the total volume. But for the question case, it asks per unit length, so we can make L equal to 1. Okay. So let me make some changes. We use prime for the quantity per unit length equal to Q over L. And now when you do the volume, this volume has to be equal to pi d squared over 4, which is the cross-section area of the cylinder, multiply L, and the L will be cancelled. Okay, so the Q naught prime, the maximum amount of heat being transferred per unit length is equal to rho multiplied pi d square over 4 multiply 1, because L cancelled, so you end up with a 1 unit. Yeah, multiply C multiply the temperature difference. So that's one point I want to make. Okay, so you can assume the length to be L and then cancel out L, or you can just use 1. But when you write the notation, you have to use prime for the per unit length. Another comment I want to add is the unit for the thermal energy being transferred per unit length has to be joule. Since it's per unit length, so it's joule per meter. Okay. So that's the second comment. The unit has to be consistent with the notation you use. If you use Q prime, the big Q prime, it has to be joule per meter. The third point I want to make is the negative sign. We have a minus sign. It just tells you the heat is being into the cylinder. Remember the sign convention? If it's out, we have a plus sign. So Q is positive if the energy is out of the object. Okay. So here we have a minus sign, indicate heat being added to the cylinder. Okay. So this is a pretty straightforward example that involves LHC method. For the same problem, we can solve it using exact solution. Since it has a simple geometry, it's a long cylinder. So we do have an exact solution for a long cylinder. Okay. So let's solve the same problem using the exact solution. Now, to simplify the solution process, let's assume the Fourier number to be greater or equal to 0.2. So we can use one-term solution. Okay. So this is the assumption. Okay. We assume right now we don't know the Fourier number. So later on, once we have found the Fourier number, we have to come back to check this assumption. Okay. So the one-term exact solution for the center line is right here, 5.52C. So theta star naught, what's defined as T at the center, so I equal to 0 at T minus T infinity over Ti minus T infinity. Okay, so plug in the number here, so 800, 1200, 300 minus 1200, so equal to 4 over 9. And make it equal to C1 e to Z1 square Fourier number. Okay. So now immediately we need to find C1 and Z1. So to find C1, Z1, we rely on the table. And to use that table, we have to compute the Biot number. The Biot number in this table is defined as H multiplied the radius R0 divided by K. Okay? So this Biot number is R0 multiply H over K. So compared to the Biot number we have found earlier based on the characteristic length, this is L sub C is 1/2 naught. So for the current Biot number, it's R0. So the Biot number has to be twice of the Biot number based on the characteristic length. So or you can just plug in the numerical value and calculate it. But it should be equal twice of Biot number based on the characteristic length. And we have found this value earlier. So 2 multiply 0.0488 and equal to 0.0976. Okay, so that's the Biot number. And if we go to this table, we have the Biot number between 0.9 and 0.09 and 0.1. So in theory, we have to interpolate to find the Biot number, to find Z1 and C1 at this Biot number. But in the interest of time, since this number 0.0976 is very close to 0.1, we just pick these two for convenience. Now, I will allow you to do the same during the exam, but when you work on the homework or outside class quiz, I will prefer you to use interpolation to find a better value for theta 1 and C1. Okay, so we found theta 1 equal to 0.4417 and C1 equal to 1.0246. Okay, so now we can plug into this equation. So 4/9 equal to C1, which is 1. So I just use C1. So it's a this is known. So E minus Z1 square for the number. So for the number is the only unknown. Okay? So we can easily solve for the Fourier number. And it turned out to be, let me check I have the final result at the very end. So 4.356. So if you did your math correct, then the Fourier number should be equal to 4.356. Now, before we proceed, this is a good time to check your assumption. So this Fourier number is greater than 0.2, so the assumption is valid, which means the one term is okay. So you have to add this sentence when you work on the one-term exact solution. So if you use one term, I will look for this sentence. Okay, and if you miss this sentence, I will take a few points away. So this is very important. So if you end up with, let's say, Fourier number equal to 0.1, then you have to, you have to add more terms. The one-term solution will not be accurate. Okay? So very likely you will get a Fourier number greater than 0.2 because I don't want you to, to spend much more time adding additional terms. But still, as a good practice, you have to verify the assumption you made earlier. Okay, so now we are safe. We can proceed to find the time. So T is related to the Fourier number by the definition of the Fourier number, alpha T over R naught square. So T equal to the Fourier number multiply R naught square, or we can use the diameter. So diameter square divided by 4 divided by alpha. Okay. So we have the Fourier number, we have the diameter, we have the thermal diffusivity alpha. So the math is very straightforward. So the final result for the time is almost exactly equal to 900 seconds. Okay. So that's the time required using the one-term exact solution. Now compare this solution with the result of Lhc method. The one is 900. The Lhc method produced 859. So how many percentage of difference? Let's do a quick comparison. So 859, 900 divided by 900, multiply 100%. So we use this to calculate the percentage difference. So that's 42 divided by 900. So it's close to 5%, slightly less than 5%. Which is what we expected because the Bill number based on the characteristic length is about 0.05. Okay, so when you get a Bill number based on characteristic length equal to 0.1, we expect to have 10% difference. 0.05, yes, the difference expect to be 5%, around 5%. And I will trust the exact solution more. So that's a solution using the exact solution method. Now for the heat transfer rate, are not heat transfer rate. The thermal energy being transferred per unit length is equal to rho multiplied volume pi d square over 4 multiply 1 because it's for unit volume. Okay? Multiply C multiply Ti minus T infinity. So this produces the maximum amount of thermal energy can be transferred. Multiply. Now you have to look up the solution. So 1 minus 2 theta star naught divided by theta 1 multiply a special function which is called base function of first order at theta 1. So we have theta 1, we have 0 star naught which is 4 over 9. Okay, and we need the value of this basic function. As I said, you can easily find it from online. I will wait until we get to another special function, and then we will, see how to find the special function values. Okay. And I did the math earlier. So the amount of heat being transferred at t equal to 900 seconds is equal to 1.697 joule per second, joule per meters. So compared to the result of LHC, it's also very close. So LHC produced 1.664. 1.664, that's from LHC, and the exact solution produced 1.697. So, pretty good. Okay. So so we answered both questions. One is time, one is the amount of heat being transferred. And compare these two methods, LHC, it doesn't differentiate the temperature inside the cylinder. So at the center, 800 Kelvin, the surface also 800 Kelvin. At the middle, anywhere, it's always 800 Kelvin. That's Lhc method. It won't allow us to find the temperature variation inside the cylinder. But for the exact solution, the center is 800 Kelvin. Now the surface temperature has to be greater than 800 Kelvin because the ambient temperature is much higher, 1200 Kelvin. So we expect surface temperature to be between 800 and 1200. So how do we determine this surface temperature in the exact solution? So this is the exact solution. Okay. We have to use the solution 5.52b. So let me write down the solution. Theta star naught multiply a basic function r star theta 1. Okay, so we have to use this equation to find the temperature of the surface, and theta star can be related to the surface temperature by Ts minus T infinity, Ti minus T infinity. Okay, so T infinity is 1200, Ti is 300. Okay, so the only unknown is T sub s. And on the right side, theta star naught, we already have it 4 over 9. If you check the calculation we did earlier, it's 4 over 9. And this special function is a basic function. We can find it either online or from the table. Now, what is this r star? That's the dimension is coordinate equal to r at the surface, which is r naught, divided by the radius of the cylinder, so equal to 1. So this is the dimensionless value, r star equal to 1 at the surface. Okay. So based on this, the right side can be calculated. It's just a numerical value, and we can solve for Ts. Okay. And again, this surface temperature has to be between 800 Kelvin and 1200 Kelvin. Okay. I don't have the numerical value for this T sub s, but you can try to solve it yourself. So that's the example, but we can add a few follow-up questions. So one of the follow-up questions is, what is the mean temperature? We know at this T equal to 900 seconds, the temperature at center is 800 Kelvin. The surface temperature can be solved using this equation. But what is the mean temperature, T average? So what is this so-called equilibrium temperature or the mean temperature, T average, when the center reaches 800 Kelvin? Okay. And the mean temperature has to be greater than 800 Kelvin. And we can determine the mean temperature or the average temperature based on the amount of heat being transferred. So Q T, if we use the mean temperature, it should be low, let's use prime, pi d square over 4 multiply 1 because it's per unit volume or per unit length, multiply C, multiply Ti minus T average. Okay. So that's a amount of heat being transferred in terms of mean temperature or the average temperature. But this also equal to the Q naught prime, which is pi d square over 4 1 multiply C Ti minus T infinity. So this is Q naught prime. Multiply for cylinder, use the solution in the table. So it's 1 minus 2 theta star over theta 1. Okay. Multiply Bessel function of theta 1. So we have this relationship. So this part is based on the exact solution. And this part is just based on the energy balance, the temperature difference multiply MC has to be equal to Q. Okay. So using this equation, we can determine the mean temperature T average. Okay. So that's how to solve the average temperature. Another follow-up question can be, find the time when the surface temperature of the cylinder reach 800 Kelvin. And in the original example, we find the time when the center line reach 800 Kelvin. Now we want to know how long will it take for the surface temperature to be 800 Kelvin. Okay? And to solve this problem, we've just utilized the exact solution. So now we have theta star at r star equal to 1. The time is unknown, so the Fourier number is unknown. And we assume one-term solution. So C theta star naught multiply J1 R star theta 1. Okay, so we just make R star equal to 1. Theta 1 has been found, so we can actually determine theta star naught. Okay, and then we relate theta star naught with the Fourier number using this definition. So we can find the Fourier, and then from the Fourier number, okay, check Fourier number whether if it's greater than 0, greater than 0.2 or not. So find the Fourier number and then find the T. So that's these are the procedures if you want to find the time when the surface temperature reaches 800 Kelvin. Okay, We spent 40 minutes to cover to give a review of part 1 of chapter 5, and also we did one example using the 2 different methods. Okay. Next, we are going to study the transient conduction in a semi-infinitive solid. Now, the solution for semi-infinitive solid is much simple. So it won't take us too much time. So here is the configuration or the setup of the problem. Suppose we have a very large solid. The left side is it can have different boundary condition. Okay? So we have different boundary condition applied to the left side, and we assume the x coordinates start at the left side. So x equal to 0 corresponding to the surface at the left side. Okay? And we want to know what is the initial temperature of the solid is T sub I, which is given, and then we apply certain boundary condition. For example, we can heat in the surface at the x equal to 0. So at the surface, we add heat. Now the temperature of the solid will change with respect to time t. And we want to know what is the temperature at a distance x away from the surface at a particular time t. So what is this temperature at this location at a given time t? Okay. So that's the question we want to find. And as one of the application can be, suppose we have a ground, and the ground can have different boundary condition. We can heat the ground surface, or we can have a convection taking place at the ground surface. And initially, the ground has a temperature T sub I, so that's at T equal to 0. That's the initial temperature profile inside the ground. And once the action at the boundary, at the ground surface taking place, now we have a transient conduction inside the solid, inside the ground. And we want to know what's the temperature at a distance x below the surface of the ground, below the ground surface at time t. So these are the type of applications that we can solve using the solution for semi-infinity solid. Okay, so we can consider them as semi-infinity solid. Now, if the time t is small, then the thickness of the wall doesn't need to be very large. Okay, so if you want to find the temperature at a short time t, then the thickness of the wall doesn't need to be very large. You still can assume the solution for semi-infinity solid will be a good approximation. Okay, so depending on the time, if t is short, if t is small, then the wall can be seen, and the solution still will be valid. Okay. And in general, to solve this transient problem, we start with the heat equation. So here I have the heat equation. Okay, and it's a PD equation, partial differential equation, because t depends on 2 variables. One is x, the other is t. So it's a multi-function variable. And to solve this problem, we know it's a hard problem. Partial differential equation always very difficult to solve. And then, so that's a governing equation. And the boundary condition, as I said, we can have different type of boundary condition. Here, there are 3 cases. Case 1, when we have constant boundary condition at the surface. So we hold the surface temperature at a constant T sub s. And for constant temperature boundary condition, let's say start at T equal to 0, we have the initial temperature T sub I. So that's it. Everywhere inside the solid, the temperature is T sub I. Okay, so that's corresponding to T equal to 0. As T increase, the temperature, gradually increase. Okay, so we will have this profile, and you will see the slope the slope drop as t increase. That's because the slope is dt over dx. When as time move on, the temperature near the surface become closer and closer to T sub s. So the temperature gradient drop. So as a result, the slope will increase. Okay. So eventually, as T approach to infinity, after a long time, the temperature of the solid will be equal to the surface temperature T sub s. So this is a extreme case when T approach to infinity. So okay. So that's the first case when we have a constant surface temperature. The second case is when we impose a constant heat flux, Q double prime. This constant heat flux can come from, for example, radiation. So if you put a surface under sunlight, and the sun will provide radiation flux, and we can assume the radiation flux be a constant flux. So in that case, the flux equal to constant, and we make this flux equal to the conduction flux. So that's the boundary condition. The given flux equal to the conduction flux. Q double prime is constant. K thermal conductivity is constant. So it requires the temperature gradient partial T over partial x to be constant. So that's why you see the slope had to be the same. So it had to maintain the same slope. Okay. So that's a boundary condition of a constant heat flux. The third boundary condition is a convection boundary condition. So for convection boundary condition, let's look at the temperature gradient partial T over partial x. So K multiply partial T over partial x, the conduction flux equal to H multiply T infinity minus T. That's a convection flux. So we have convection flux equal to conduction flux. That's a boundary condition. So as you can see, the T at the surface increase. So this T increase. T sub infinity is constant. So T sub infinity minus T will drop. So the whole term will start to drop. As a result, the temperature gradient will also drop, right? So this partial T over partial x will decrease. So this is exactly what you see in the graph. The slope start with a large slope, and then gradually it drops. Okay, and eventually, after sufficient time, the slope becomes flat. You have a zero slope. Okay, so that's these are the three cases, and I have a more detailed analysis for this change of the slope. Okay. So now we have the governing equation, which is a partial differential equation. We have the three type of boundary condition. Now we are ready to solve the equation. Okay. But we use a special method. It's called Similarity method to solve this partial differential equation. We use a Similarity method. Okay. This method basically, so let me give you the general idea about this method. Okay. So we have two variables involved in the partial differential equation. One is x, the other t. So we have two variables. And we can try to combine these two variables into one variable. And the new variable is called eta. So we combine x and t into one variable by using this relationship. This is so-called similarity variable. Now, it's not always the case that you can combine two variables into one variable. It happens only to a parabolic PDE with certain special conditions. So this similarity method, it's not universal. It's only applicable to parabolic partial differential equation with certain special condition. Okay? but for us, it happened to be applicable. Yeah. So we are able to combine two variables into one variable. The temperature T originally is a function of two variables, x and t. So now we reduce this t into one variable. The single variable is eta. And originally we have a partial differential equation PDE. Since now we only have one variable, so we can reduce it into an ODE. Yeah. So that's and ODE is much easier to solve compared to PDE. So that's so this is the approach we're taking when we use the similarity method. Yeah. So these are the steps. We combine two variables into one variable. Now the form of this equation can be derived based on the dimensional analysis or other methodology. As I skipped that part. I just provide you how we what is the similarity variable in terms of x and t. So we can replace x and t using the new variable and replace the partial differential equation with the final ODE equation. So this is the final ODE equation. And it's a second order nonlinear ODE, and you can find the solution from any differential equation textbook. Yeah. And solution depends on the boundary condition. So I will just provide you the final result for 3 boundary conditions. Remember, the first case is when the boundary condition is given by a constant temperature. So if we have a constant temperature, this is the solution. And if you look at the solution we introduced, we have a new function ERF. That's called the L function. Okay? So T sub S, that's the surface temperature, what should be given. And T sub I, that's the initial temperature of the solid. And the T at xt, that's that's a known we are looking for. Yeah, what's the temperature at a certain distance away from the surface? So x is the distance away from the surface. The second case is for constant heat flux, and we have a slightly more complicated solution. Okay? And in this solution, it involves a potential function, ERFC. That's called complementary L function. So I have the definition of these two functions. One is the L function defined as this integral. Okay? The other is the complementary L function, ERFC, which is equal to 1 minus the L function. So that's the relationship between the L function and the complementary L function. Okay? So the case 2 involves a complementary L function. Now case 3, which is the most common boundary condition, the convection boundary condition, it involves, again, a complementary L function and a potential function. So these are the exact solutions, and we got this solution using the similarity method. If you are interested, you can grab the textbook to see the details. But for us, what I want you to know is how to use this solution. Let's look at these two special functions, L function and the complementary L function. In this graph, the red curve is for the L function. As you can see, at eta equal to 0, when eta equal to 0, the lower limit is 0, the upper limit is 0, so L function has to be 0. Okay? And as eta increases, L function quickly approaches to 1. Even at eta equal to 2, it's almost very close to 1. Okay? And so that's a trend of L function. For complementary L function, it's just 1 minus L function. So at eta equal to 0, the complementary L function is 1. As eta approaches to infinity, this complementary L function approaches to 0. So these are the special case when L function at 0 it's equal to 0. At infinity, it's equal to 1. For the complementary, at eta equal to 0, it's 1. At infinity, it's 0. Okay. There will be one question ask you, to ask you about the error function and the complementary error function. Okay, so that's a solution of 3 cases for the transient conduction in a semi-infinity solid. For case 3, instead of using this very complicated exact solution, we can plot chart in advance and use the chart to do the calculation. Okay, so here is the way that we plot the chart. Okay? So this is how we plot 5.8. So 5.8 is the solution for bounded condition with a convection surface bounded condition. Okay, so basically we can provide the solution for case 3 using this chart. Now, how can we use this chart? So first, let's look at the exact solution. So t minus t sub I over t infinity minus t sub I equal to error function minus a potential function multiply another complementary error function. So let's first define x over 2 square root alpha t as a. So I'm going to call this as a and call this h multiply square root of alpha t over k as b. So that's my b, that's my a. Okay. So now let's look at the term inside the exponential function. So hx over k. So if you pay attention, hx over k is equal to a multiply b. So if you use a multiply b, alpha t cancel out. So you have hx over k and multiply union multiply 2. So actually it's 2 multiply ab, right? So 2 and 2 cancel out. So now you end up with hx over k. So hx over k is equal to 2 multiply a multiply b. Okay. Now h squared multiply alpha t over k squared, that's exactly equal to b squared. So in the exponential function, the term is just 2 multiply a multiply b plus b squared. So you see the left side of this exact solution only depends on a and b. So it's a function of a, b. So left-hand side, that's the left-hand side, equal to a function of a and b. So we can calculate a and b, and then we can determine its left-hand side. Okay. So this is exactly what the chart is about. The s-coordinate is equal to a. These red curve corresponding to different b. Okay. So we calculate a first, and then we calculate b, and then we can determine this temperature ratio. This temperature ratio. So that's how we utilize this chart. Okay? So that's how we define the A. So we calculate the A, and then we calculate B, and then we go to the chart to determine this temperature ratio. And from this temperature ratio, we can find the actual temperature at the location X and at a specified time T. Okay. I want to add a very important comment here. When you have a convection bounded condition, it requires a convection coefficient H. And when H is extremely large, so many times it doesn't tell you it's go to infinity, it just tells you extremely large. So if you have extremely large edge, then the convection boundary condition can be reduced to a constant surface temperature boundary condition. And the constant surface temperature is equal to the T sub infinity. So what you mean, the thermal resistance of convection approach to 0. So the temperature of fluid and the surface basically equal. Okay, so the surface of the boundary will be equal to the fluid temperature. Okay? And we also can prove that using the boundary condition equations. So we have the conduction. So let's look at the boundary condition at x equal to 0. So we have conduction heat flux. It had to be equal to the convection heat flux. The convection is into the surface, so T surface minus into the surface, so T infinity minus T surface. So as H goes to infinity, the heat transfer rate cannot go to infinity. It had to be finite. So finite value equal to infinity multiply, it had to be a very small number, okay? Very small number. So T infinity minus T surface had to be very small. So essentially it says T sub S had to be equal to T infinity. Okay? So that's a consequence when you have a very large convection coefficient. So you can use a constant temperature, constant surface temperature solution. So when you have a very large edge. Okay. Next, by using the solution of constant surface temperature, we can determine the temperature at the interface of two very large solids. So suppose we have two large solids. One is A with the initial temperature T sub AI. So that's a solid A. The other is solid B with the initial temperature T sub Bi. And we place them together so to create a perfect contact. So we neglect any contact resistance. And we want to know what's the temperature at this interface. And to find this T sub S, we can consider the transient conduction with a constant temperature of T sub S. So the solution for A, if you go to the table, you will find this is a solution for the temperature, this is a solution for the heat flux. So let's utilize this solution for the heat flux. So Q double prime S at A, at the A side, equal to Ka multiply T sub S minus Ta sub I divided by square root of pi alpha A multiply T. Okay, so that's a conduction heat flux at the A side. And it has to be equal to the conduction flux at the B side. The conduction flux had to be continuous at the interface. And direction had to be from the interface into B. So we have to use Tbi minus T sub S. This K had to be the K of the solid B, so K sub B, divided by pi alpha B T. Okay. And we can simplify this equation by cancel out alpha, pi, and T. And after you rearrange this equation, you can solve for T sub S. You see, T will be cancelled. The solution is independent of time. So this T sub S actually is independent of time. And I have the solution here. So it's a simple derivation. Okay, this is very easy to get. So that's a interface temperature T sub S. Another form, we can replace alpha with rho C using this definition of alpha. So if I replace alpha by K and rho C, I have this formula for the interface temperature. This is the one you will see on the textbook. Okay? But these two equations are identical. They are the same. Now, one example is if you use a finger to touch either a concrete surface or a couple block, okay? And we want to determine the interface temperature for this case. One is when you use a finger to touch a concrete block. The other is when you use a finger to touch a couple block. And we just, plug in, use the property and plug into this formula to find the interface temperature. And I did the calculation, and it's for the concrete block, I found that the interface temperature is 27. Here, the assumption is my finger has a temperature of 30 Celsius. The block, whether it's a concrete or couple, the initial temperature is 24. Okay, so the interface temperature has to be between 24 and 30, depending on what type of block. If it's a concrete block, I found the interface temperature to be 27. If it's a couple block, the interface temperature is very close to the solid temperature, 24. So that's why, when your finger touch a metal such as a couple, you feel cold compared to when you touch a concrete or wood surface. Yeah? And the reason is because the thermal property difference. So this is a nice example to explain, even the temperature of the two blocks are exactly the same, both of them equal to 24, but your feeling is totally different. It depends on the material. I have 3 minutes left, so let's see if we can solve this example. Let's look at the problem statement. So a thick steel slab, so this is a steel slab property given here. Initial temperature T sub I 300 Kelvin is cooled by water jet. So we have a water jet heat the surface, create an extremely large convection coefficient. So that tells us we can use a constant surface temperature. And T sub S equal to the water temperature, 25 Celsius. Okay, so H is not even given. Okay, they just tell you the H is extremely large. So don't use convection boundary condition. Instead, using the constant temperature boundary condition. Assume the surface. They add another statement. Assume the surface is maintained at the temperature of water throughout the cooling. So that's the temperature, 25. How long will it take for the temperature to reach 50 Celsius at a distance 0.25 meters away from the surface? The initial everywhere T sub I is 300 Celsius, very high temperature. And we use low temperature water jet heat the surface. Now the steel slab will start to cool down. And we want to know at 0.25 meters below the surface, when the temperature reaches 50 Celsius, what is the time required? Okay, so using the exact solution, let me copy the exact solution. And here is the exact solution. So in this exact solution, we have surface temperature 25 Celsius and T sub I 300, and we want to have this T equal to 50 Celsius. And X is 0.025 meter. Alpha is given, so T is the only unknown. So, and the only thing is, there is an error function involved. So now it's time to show you how to find the error function. By the way, for today's in-class quiz, I already added 5 minutes. So let me finish the last part, which is to use the online calculator to find these special functions. Okay, so the website is called wolframalpha.com. So let me share the website with you. So, okay, so this is the website I was talking about, the Wolfram Alpha. So let's say you want to find, first let's find the Bessel function. So first order Bessel function, J1 at, let's say, 0.5, okay? So you hit enter, it gives you the value here, 0.24, okay? And if you need the zero order, you just use J0 instead of J1, okay? And for error function, you just type EIF. If you need a complementary error function, you type EIFC. If you need the inverse, you just type in INV error function, INV EIF. Let's say let me put some number here. For example, 0.5. INV. Okay, hit return. Now you have an inverse of the error function. Okay, so it's much convenient compared to using the table or the appendix. Okay. So let's go back to the OneNote. I think I pretty much covered the topic for today, and I think it's good. It's a good place to stop the lecture. Like,
hey, sir, can you do me a favor and scroll back to that last solution you showed us?
okay, so I will do that. So last solution. So go to my OneNote. This solution? Are you talking about this solution?
Yes, that one. Thank you.
Okay, you're welcome. Okay, so it's time for you guys to work on the in-class quiz. As I said, the due date is 12:55, so you have about 30 minutes to work on it. All right, thank you.